Okay, so let's get us started. It's a great pleasure to welcome Dan Dahlberg back to Iowa State University. Dan visited me quite a few times, maybe 3 times when I was up at Ames Lab. And I visited him a few times up at the University of Minnesota. So it's good to welcome him back to ISU. I tell you a few things about Dan. I mean, most of you know him very well, so this won't be news to most of you. But for those of you that don't know Dan so well, Dan did his bachelor's in physics at the University of Texas at Arlington. And then he did a master's in physics also at Arlington in 1972, right, Dan? A long time back? Must have been more recent. Yeah, that's right. I think so. Then he went to UCLA, where he decided to do another master's degree in physics. He must like physics, Dan. Is that right? Just keeping going on that.
Pass the exam and they give you the
Degree. All right, so he's done good. And then finally a PhD at UCLA. I won't mention the year, but it's a few years back now. After that, Dan went to University of Minnesota, where he was a research associate and then was promoted up to assistant professor, associate professor, and then became professor of physics. That was about 1990, right, Dan? Somewhere in that vicinity? A little while back. That's what it says here anyway. So round about that time. And then, of course, he was promoted up to distinguished professor in 1998. He's also been the Alfred Sloan Research Fellow, an AAS Fellow, he's also an APS Fellow, and he's won the Outstanding Instructor Award, the George Taylor Alumni Society Award for teaching, Distinguished Alumnus of the College of Science at the University of Texas, Arlington, University of Minnesota Outstanding Community Service Award, and the George Taylor Distinguished Service Award. So he's won a lot of things in his career. His main interests are, of course, in magnetism, which is what brings most of us here today. His active research includes work in spin transport and magnetic multilayers and films, and he's very interested in ferromagnetic, antiferromagnetic exchange coupling across the interfaces. In addition to this, all this research work on thin films and multilayers and spin transport, he is the director of the Magnetic Microscopy Center. Did you bring the samples along, Dan?
Pardon me?
You always give those little samples of the magnetic... Oh, okay, I'm sorry. Giving away the story already. He's been the director of the Magnetic Microscopy Center at the University of Minnesota. He's working on magnetic force microscopy techniques and applying them to a variety of outstanding physics problems. Now, I've got to tell you, Dan is talking to me about using these techniques for non-destructive evaluation. So there's another area where we have interests in common. So there it is. Dan is a very famous guy, distinguished professor at the University of Minnesota in the physics department, and it's a great pleasure to bring him down today to talk to us. This colloquium is an investigation of magnetic reversal at almost the nanoscale. I'm wondering how that word almost got in. It sounds like Dan's not too sure about whether he's really on the nanoscale or not. But it's a great pleasure to welcome Dan. And just before I bring him up here, I want to tell you that there is another lecture tomorrow afternoon at 1 o'clock in the Lully Auditorium. And that will be a more research-focused lecture, whereas this is a colloquium. So Dan, it's a great pleasure to bring you back. Please welcome him to the colloquium.
I don't know where you got your information, but you know more than I know. So it's how would I know? So it is my pleasure to be here. There we go. It's as David said, there's been several times when I've come here to visit, and it's always great fun. I'm not sure I'm somehow. Nope. Somehow my little thingy's not working right. What's the matter with you? Now it's working. So this is what is known in theater as an intimate audience. So y'all should come forward a little bit. I don't spit. Come on. Let's get you in the first 4 floors, in the first 4 rows here or something, right? I think there's space. Now I can tell you the truth. I do spit when I talk, so it's really nice to be here. like David said, I've come here several times and to visit with him, and I'm really happy that now he's back at Iowa State, because the last time I wanted to see David, I had to go to Cardiff, and so that was about a year ago, and so now I don't have to travel nearly as far to see him. And I'm sure y'all are all happy that he's back here. Now this is the slide that goes along with the talk that I thought I was going to give. Y'all are going to have to excuse me because I'm not infectious, but I'm getting over a cold, and so every now and then I'm going to have to cough and clean that stuff out. This is going to be the first slide, and it was called A Voyeur's Tale because this was some research that we had done where I was never happy. We never really extracted the physics from it, and it was more just an observation, so we never published it. My thesis advisor, Ray Orbach, said you can't publish data. So we never published data, right? So that was what I was taught, so we don't publish it. But then when I was getting ready for this talk, I remembered something that somebody had told me, and so I thought, well, about a month or so ago, I started looking back into it. And what we were interested in is to take stadia-shaped particles and reverse the magnetization from where the magnetization is pointing to the right to where it points to the left. And the surprise we had in here is that in this reversal process, in small particles, you will nucleate a vortex. And I'm going to explain what a vortex is to you. You nucleate a vortex, and then that vortex propagates across. But when you make the stadia longer, you all of a sudden have spontaneous nucleation of vortex-anti-vortex pairs. And this is the part that we had troubles with. There's a particular asymmetry in this problem that we never understood. But now, when I started getting ready for this talk, I started going back and looking at some stuff, and now we're actually writing it up for publication because, in fact, the real title is Magnetic Reversal at Almost the Nanoscale, Conservation of Skyrmion Number Effects. So it turns out that what with this asymmetry we've been hunting for and trying to understand, it looks like it comes from conservation of Skyrmion number, whatever the hell that is, but I'll tell you what that is as we go along also. It'll be at the very end. So in fact, most of the talk is going to be getting us up the micromagnetics and magnetic force microscopy. So for those of y'all that are expert in this, you can sleep for the first half. And then at the very end, when we start doing the stadia, I'll remind you to wake back up, because that's when it gets good, when we get to this vortex-anti-vortex pairs. Now, because this is a general audience, I prepared a lot of background information for this, and I'm going to spend a number of slides going through it. But the bottom line is, if I have two magnetic states, so here I have a magnetic moment pointing down, here's one that's pointing up, and I want to be able to get over this energy barrier to go from where it points down to where it points up. So this is the angle that the magnetization makes in this direction, and that's the energy, and this is the barrier. For decades now, we've understood the reversal process for single electrons. So that's something that was done back whenever people were doing spin resonance. That's the basis for magnetic resonance imaging. So this is a problem that we understand quite well now. Bulk systems, things that occur, say, in the real world, are too complicated for physicists. It's too nasty. So we avoid those things. So what we've been looking for are model systems where we can understand this process in a more fundamental sense. And so the systems that I make are made lithographically, where we can control the dimensions, we control the aspect ratios. For a while I did this by harvesting magnetosomes out of magnetotactic bacteria. So there's been a whole evolution in this, in what we do for our model systems. And but it's this energy barrier that's all important, and how that energy barrier depends upon the magnetic field. And all the energies that control that energy barrier are right here. In all of magnetism, all the different variety of phenomena that you see, you only got to worry about four energies. The Zeeman energy. That's the energy when you put a magnetic moment in an external field. The dipole energy, that's the interactions between dipoles. Spin-orbit interaction, this is the one that makes magnetism technologically useful. That's the only thing that couples spin space back to real space. And then the exchange energy. Now, I'm going to go through these one by one. So this is the background. Again, like I say, for the experts in the field, you can doze off. The starting, and actually, of these four energies, three of them are the same, which makes it even easier, right? Magnetism is not a tough subject. The Zeeman energy, I have a magnetic moment. This could be my electron, for example. I place it in the presence of a magnetic field, and there's an energy that depends upon the angle between the magnetic moment and this field. You already know this. You take two bar magnets. If the north poles are together, you can't push them together. If there's two south poles, you can't push them together, but a north and south pole, they're attracted to each other. So I put my little dipole moment in the presence of a magnetic field. If the north pole is up against this north pole, that's a high energy state. South pole is down this way, it's a low energy state. Now for an electron, it has a magnetic moment. And for what we're on a microscopic scale, its magnetic moment comes from two places. One is that it has a magnetic moment from its intrinsic spin. An electron has charge, right? So and we also know that it has spin, so it rotates on its own axis. So it's like a little bitty current loop. And in your freshman physics, you know that if you take a little current loop that encompasses some area, you'll have a magnetic moment where that magnetic moment is the current times the area. So you can think of one useful model for an electron. It's a point particle, but let's think of it as being distributed in space. It's spinning on its own axis. It's got a negative charge, so that's like a little current loop. So that's its magnetic moment. It's an intrinsic magnetic moment. Now, electrons also partake in the chemistry. They're in the atoms. They're in different quantum mechanical states. And some of those states have angular momentum, so you can think of the electron not only spinning on its own axis, but you can think of the electron going around a circle around a nucleus. So it can also have a magnetic moment that really looks classical, where the magnetic moment is associated with the angular momentum. So I could have one related to the spin and one related to the angular momentum. And we combine these together to talk about the total magnetic moment of the electron. So that's what I have for this Zeeman energy. Now, the next one, this dipole interaction, is nothing but the Zeeman energy again, except I know that if I have a little current loop like this, so this would be like the spin of my electron, it produces a magnetic field. So my electron that has its magnetic moment that was spinning from its spin, not only does it interact with the magnetic field, but it produces a magnetic field. So that means if I have another electron over here, it can see the magnetic field produced by this little current loop, by the other one. That's the dipole-dipole interaction. So it's nothing but the Zeeman energy again. We're on energy 2, but it's still the Zeeman energy. And it turns out that the energy between those two dipoles goes like 1 over r cubed. Now, you can imagine if I have a cube of material that's a centimeter on a side, if I have to add up this dipole interaction between all the spins in there, that's got to be a pain, right? So you never do that. Turns out that you can look at the geometry of the sample and lump everything together, and it's called the demagnetization energy. So I can take a sample that looks like this, and I can imagine all the magnetic moments point in one direction like I would for a ferromagnet. And thinking about it in terms of electrostatics, that means I've got a positive charge up here and a negative charge down here. North pole's at the top, south pole's at the bottom. But that means for my dipole-dipole interactions, I'm sticking two north poles together and two south poles together, right? That's cost me energy. It doesn't like that. Just the same way as separating the charge on a capacitor, that costs me energy. So the sample will try to break up into smaller and smaller domains. In this case, when it's all a single domain, we would talk about its demagnetization energy. You can calculate for different geometries, but that energy always wants to demagnetize it. And one thing that's important is that it's long-ranged. So those are the first two energies. The third energy is the spin-orbit interaction. Now remember, we talked about how the electron has a magnetic moment due to its angular momentum. So think about it spinning around the nucleus in a simple circle. So it's going around like this. If my electron is egocentric and it says, I am the universe, it sees the proton or the nucleus spinning around it. The nucleus has a positive charge. So from the electron's point of view, it sees this positive charge of the nucleus going around it in an opposite sense. This positive charge going around it in the opposite sense is a little current loop. That will give rise to a magnetic moment, and my intrinsic spin of my electron can interact with that magnetic moment. So now I've got another magnetic field. It's still the Zeeman energy. It's just now it's produced by its orbital motion, where from the electron's point of view, this positive charge is going in a circle around it. Now again, just like with the dipole-dipole interactions, you don't want to have to sit there and add this up for every electron that's inside the system, do you? I got 10 to the 23rd electrons. I don't want to have to deal with this. So we lump them all together, but remember now, most electrons in a solid, let's take something that's ferromagnetic. Let's look at iron. The electrons in the iron that are magnetic are d electrons. So I have these 3 d electrons sitting out there, but the 1s electrons, the 2s electrons, the 2p electrons, the 3s electrons, 3p electrons, they're all paired up. All the electrons in all the different states are paired up. So if I do this calculation, I get 0, right? For every one up, I got one down. So for every one that interacts with the nucleus in this direction, I got another one that's pointing in the opposite direction. So the energies all cancel each other. The only electrons that are relevant are the ones that partake in the chemistry. They're these d electrons. And so if I look at these d electrons, if they're partaking in the chemistry, if they're what determines the symmetry of my solid, these d orbitals have to align up in particular crystallographic directions, right? If they do that, I can just add those electrons up. I can make sure I use the symmetry of the crystal, and we actually call this the anisotropy energy. So this is now a magnetic energy. It's a Zeeman energy, but we call it the anisotropy energy of the crystal. And this is what makes magnets technologically useful. This is what couples spin space to real space. If I take hydrogen and I've got an electron sitting around there, that electron can point in any direction in space. If I have a hydrogen solid, it can point in any direction in space. There's nothing that couples spin space back to real space. The spin-orbit interaction couples spin space back to real space. Because of the symmetry of these d orbitals and the way they set up in my crystal, now I have an energy that wants my spins to point up, or point to the right, or point to the left. That means then that if they can produce a magnetic field, and that field can be as long as that field is smaller than the demagnetization field, the dipole-dipole interaction, I can have a permanent magnet. If it wasn't for this, no permanent magnets. But it just comes from a Zeeman term, again, that we all lump together into this anisotropy energy. Now I'm going to swindle you a little bit. I apologize for that. But for the exchange energy, this is a swindle, but it has the right flavor in it. Okay, so it's a nice swindle. And I told you it's a swindle. I take a cube that looks like that, and I got 10 to the 23rd cubic electrons per cubic centimeter. So this is iron, cobalt, nickel. I don't care any of them. Now, quantum mechanically, each electron has to have its own unique quantum number. So let me just simplify this by a particle in a box. Here's my energy levels. Ground state, first excited state, second excited state. And I know in each one of these states, I can put 2 electrons. So in this bottom one, I got 2 electrons. That one, I got 2 electrons. This is what we do with when we're talking about the first quantum mechanics class and things that you do. And you fill up all these levels with electrons till you've run out of electrons, and that determines your Fermi energy for you. We always neglect this, but in fact, those 2 electrons that are in that ground state is made up of only kinetic energy. In the middle of that box, there's 0 potential. At the walls of the box, I have an infinite potential, so it's only kinetic energy. What I'm neglecting is the fact that my 2 electrons sitting in there have a charge. They have a negative charge. So there's a Coulomb interaction between those 2 electrons, and they repel each other. So in fact, if I can take one of those electrons and elevate it up to the first excited state, I've reduced my Coulomb interaction. It costs me kinetic energy, but I've gained Coulomb interaction, or Coulomb energy. Now, since they both went into this bottom energy level with the same, with opposite spin directions, I've just elevated that one up there, keeping it spin up. So to make sure that this electron can't pop back down there and cost me energy, I can take my electrons that I'm exciting and put them with parallel spin into higher levels. So now this has cost me kinetic energy. It's impossible for this one to pop back down because they have parallel spins, and it's gained me Coulomb energy. And in fact, this is where the exchange energy comes from. I take electrons, close to the Fermi surface, close to the highest energy levels that are occupied in that box. And if I have, and this is why the transition metals are important for those of y'all that are into this, because I get a big densities of states right at the Fermi energy, and then I can elevate them to a little bit higher kinetic energy. So because there's a lot of empty states, I can push them up a little bit. Doesn't cost me a lot of kinetic energy, but all those that I push up, I gain Coulomb interaction, right? So just these states are, the electrons are still all in the box, but when I calculate the Coulomb energy, because these states are orthogonal to each other, that helps reduce that Coulomb interaction. So even though they're still in the box, they're spatially removed from each other, if you like. Now, the place where this is a swindle, you would think that if I have a 1 centimeter cube, that this exchange interaction from here to here is still important, and it's not. The exchange interaction is actually on a short length scale, and maybe for those of y'all that have had a solid state class, when you do the tight binding model, when you work out all the terms, you'll actually get an exchange term in the hopping integrals that where you can actually see where it comes from a nearest neighbor interaction, which is a better picture. But this has the right stuff in it. It's a Coulomb interaction that's promoting this, and that's why. Let's take my 2 electrons from the dipole-dipole interaction. If I have 2 electrons that are 1 lattice constant apart, a couple of angstroms, how big is that magnetic interaction? How big is the dipole-dipole interaction? Any takers? Students. I won't embarrass the faculty. Bruce. No, I'm not going to embarrass the faculty. No. So from nearest neighbors, how big would you guess? The dipole-dipole interaction, just from their magnetic moments. You look like a student. You a student? You a student? Nothing to do with it. So, just classical. This is just the classical dipole-dipole coupling. For a spin 1/2 electron, a couple angstroms apart, it's a 1/2 Kelvin. Now, Bruce, what did you ask? The Curie temperature is over 1,000 Kelvin. But the dipole-dipole interaction is only a 1/2 Kelvin. So it's clear that this dipole-dipole interaction has nothing to do with ferromagnetism, except that the electrons have a spin. That makes them fermions. They have to have unique sets of quantum numbers. That means that I have to make sure they don't fall down into the same state, I have to have parallel spins. And it's just an accident that it happens to give me this magnetic moment. And this interaction that pushes that guy up is in Coulomb energy. So now all of a sudden, I've got a big energy. I've got something that I can play with that's 1,000 Kelvin now. So that's where the exchange energy is, and that's where my swindle was. Okay. So just as a comparison, my dipole-dipole interaction, which is incredibly weak, across this big solid, still wants to break it up into domains, even though it costs me exchange energy. But it's because that exchange energy is very local, so if I make these transitions rather gradual, that will happen, right? So I don't pay out all the exchange energy between nearest neighbors. I let it sort of slide away, right? So it'll still do this, so that puny little dipole-dipole interaction will still break up a ferromagnet into domains, even though it's nothing compared to the exchange energy. Okay, so that's the reason why I'm doing this, is that all of these things combined are the energies that give us our magnetic states, and we're not able to just minimize those energies. Turns out to do calculations, you have to, because a single spin follows a torque equation. It precesses in a magnetic field. So we want to follow the magnetization or magnetic moment as it precesses around a magnetic field. But this field is a fictitious field, and it's the way you do often. You take the derivative of the energy with respect to the relevant property, right, for magnetization, and that's our effective field. And that energy comes from all these magnetic energies. And for my research, and you'll see this later, it's not only to be able to calculate the energies that I get, but also to be able to interpret our images. And you'll see that this is really very important. By every one of my microscopes, I have 1 or 2 computers that sits there that does this calculation. And the code that I use, that I bought from Mike Scheinfein, cost me $5,000 per computer. And I probably have 50 keys, or 5 keys. I've got $50,000 invested in just cranking out that one differential equation. And this last term, this is the precession term, right? That's my normal torque. This is just a damping term to make sure it finally decays away. So this is phenomenological that goes in there. Okay. Now, let's do scanning force microscopy. Y'all have been doing scanning force microscopy since you were babies. It's just that simple. The first force microscope was your finger. So if you take your finger and you run it over a surface, you have sensors in your finger that tell you what the pressures are. You can actually feel the texture. And that sensor is sending information to your computer to tell you about that so that you can interpret it, so you can run over different surfaces and you see different things. I can scan my finger over this pushing hard. I can scan my finger over pushing very lightly. And I have a servo mechanism that's controlled by my computer, so I can raster, so I can really get all the information. And your finger's pretty good. Your finger has a vertical resolution of about 1/10 of a millimeter. I need to see the hands of the students. Who's a student in the room? And don't be shy. Come on. Don't look around. You know where you don't have to see if the next guy's a student. Who are the students? Okay. For y'all, I want y'all to tell me this next force microscope, because we did not jump from our finger to atomic force microscopy. We took it in stages, and along the way, we developed this force microscope. Got a vertical resolution of about 10 microns. What kind of a force microscope is that? All of your grandparents had one. Huh? This is a picture of the microscope. Huh? Gramophone. Oh, that's even older. So it's a phonograph record, right? It's a phonograph. So this is the cartridge right there. These are the grooves in the record. And it took the topography, and rather than change it into a false color image like we do, it changed it into an auditory image that you could listen to, right? And you can, for the life of me, I've looked at this cartridge. I don't quite understand it, but if you look, the topography on the 2 sides of these grooves are different. So this is a stereo record, but I don't know how this cartridge was actually stereo. But that's got a vertical resolution of 10 microns, which is not bad at all. About an order of magnitude better than your finger. Then what we did, we wrote on the backs of the semiconductor industry that learned how to do micromachining. They were able to micromachine our fingers out of single crystal silicon, so that down here at the very tip, one atom was sticking out a little bit farther than all the others, and then your finger can now see atoms. That's why they call them atomic force microscopes. Vertical resolution of 0.01 nanometers. Now, I've been doing force microscopy off and on for 15 years, 20, I don't know, long time. You know how many times I've seen atoms? Maybe twice. They call these things atomic force microscopes, and they tell you can see atoms, but you have to work at this. This is not easy to do, but you can do it. You can see the atoms. Now, in addition to this, we take our fingers and we can coat them with the little magnetic films, cobalt chrome alloy on the very tip. Now, your finger has thermal sensors in it. So if the back of this chair were hot, I would not even have to touch that chair to know it was there. I could just run my finger over it, and the thermal radiation coming off the chair would be sensed by my fingers, right? So this is called non-contact force microscopy. Our magnetic tips don't have to actually touch the sample. We can run it over the sample, and then if our sample has north pole sticking out of it and this tip has a south pole, for example, it would get pulled down. if the sample has a south pole and our tip is a south pole, then it would get pushed back. So we can actually image what the fields look like coming out of our samples. And with that, y'all are expert. Y'all are as good as I am. That's all I know. Now, this was actually from an article back in ancient history now, right, that we had. And this is a single crystal of magnetite that we had on the cover, where it was cut at an angle to those d orbitals, to that anisotropy energy, if you like. And the nice thing about it is that it was a tremendous interplay, no applied fields, but it's an interplay between the demagnetization fields, the exchange field, and the anisotropy field. And of course, they wanted color for the cover. I tried to get them to do a grayscale. Because of the grayscale, you have a lot more detail. You can see these are actually square spirals. So they reflect the crystal, the cubic symmetry, where you see these square spirals going up and down the sample. Now, I've got homework for you over here. This is what David was alluding to. Because since y'all are all expert, I figure y'all can work on this. So what I have here is something I can't open. Oh, well, never mind. I'm sure that some of y'all down here have seen this before because I've been doing this for years. So you've probably already got one of these. A stack. How many times have I? What do you mean? Somebody stole this? This is something one of my graduate students came up with. So it's just a refrigerator magnet. I don't know if that's right. Say yes.
Yes, it sticks.
And this is just a piece cut off it. See the writing? Now I want you to listen to this. Can you hear that? Yes. So when my graduate student, this was a graduate student. This was the student that actually built my first MFM, my first magnetic force microscope. And he came in here, and I was just amazed. He was playing around with this. The amount of physics that's in a simple refrigerator magnet, these things that hang on your refrigerators that you never think about. And what he did, he said, look at that. And so there's a domain pattern in here to make it stick on your refrigerator that they put on there. And let me tell you that I've talked to the people that make these things. They don't know why it does it. It's magic. But it sticks on this side. But look at this side. There's nothing. There's no interaction. It has nothing to do with the white coating. Okay? So for those of y'all that don't care about the physics I'm about to talk about, y'all play with the magnets. And if you can just take one and pass it back. And people at the back row that didn't move forward, you don't get one. Okay, maybe I'll be a soft touch. Oh, you gave yours away? What a nice guy. Anyway, take one and pass them around. And there's probably... I'll give you one if you quit playing with your computer. He's in computers and I'm...
What do you want?
If I had my iPad, I'd be running it on underneath the stadium doing something myself. So it's... Everybody got one? Who doesn't have one? Oh, wow. Who else? How many more do I need? Do you have one? Oh, they quit passing them around. What is this? It's one per customer. I think he needs one. Everybody got one now? Okay, so that's what you do. I want to know what the separation is between the magnetic poles. I want to know what the magnetization pattern is in the card. And I want to know why that magnetization pattern is important. Okay. These tips have a spatial resolution about 100 to 200 nanometers. And for the work that we do, we need to improve this. And just real quick for spatial resolution, if I have a really sharp tip and two balls on this surface, I can actually see those with that sharp tip. If I have a big fat finger, I do this, I can't see those two. If I have, for instance, an isolated magnetic dipole and then three clustered like this, if I have a magnetic finger that's big and fat, it can see this. It has enough sensitivity to see it, but it doesn't have enough resolution, lateral resolution, to be able to distinguish these three. It would just see this. It cannot distinguish between these three spins and that spin, because there's this net moment over here is one up. If I have a finger that looks like that with my dipole, I can actually see all of these. And so what we did is to use contamination deposition. This is, all electron microscopes have junk in them. And you turn up the beam current and you polymerize it. And so what you do is you up the beam current, you polymerize, you turn down the beam current, you raster to see what you did, you turn it back up. Anyway, you do this repeatedly. And this is a spike that's grown on the end of a commercial AFM tip. And this is still 200 nanometers. And with this, we get resolution at least 30 nanometers. That's the smallest dipole I've ever seen. So we could have better resolution than that. Just I haven't had a dipole where the north and south poles were farther than 30 nanometers apart. I don't know. I'm not saying that. I know. All I'm saying is that I know we can see lateral resolution of 30 nanometers. Okay, now to the physics. So this is something where we're going to look at the magnetization processes in the presence of external fields in a model system, systems that we've constructed. These are soft magnetic particles with small in-plane or no anisotropy in a circular geometry. That means those three energies we talked about, I just threw one of them away. I always like to make my life as easy as possible. So we have the Zeeman energy, that's our applied field. The exchange energy, the one I swindled you on, and then the dipole-dipole interactions. But these are the only three energies that are relevant for this problem. So when I do the calculations, I can throw this one away. Just have those other ones. Now, this work came out of some work. Pete Eames was the graduate student that started doing this. And he had looked at a paper that had been published years before by Shigeto and co-workers in 2002, where they were looking at vortices in a single magnetic dot. Now, I'm going to be doing a lot of simulations. That's what you'll see better colors and better figures with the simulations. So I'm just going to start teaching about them now. But these were dots that were on the order of, say, 40, 50 microns, 20 microns in diameter. They were relatively thin, say 20 nanometers, 30 nanometers thick. They had very little anisotropy energy, so they only had the exchange energy and the dipole-dipole interaction in zero field. The dipole-dipole interaction forces the magnetization not be perpendicular to the plane, right? If it was perpendicular to the plane, all the spins would be up like this, and that would give me a surface charge of north poles on one side, surface charge of south poles on the other side. That costs me energy, right? So it wants to lie in the plane. If it lies in the plane, then in this case where it's saturated, red means they're pointing to the right. That would give me all north poles on this side, all south poles on this side. That would cost me energy. I can force that state by applying a field of a few hundred Ørsted, but it's when I'm in zero field, it breaks up into a circle like this, into a vortex. So here the blue means the spins are pointing up. The green means they're pointing to the left. Yellow means they're pointing down. And red means they're pointing to the right. So this is up, left, down, right. So it's actually a little circle. It's a vortex. The spins go around in a circle in there. And in the reversal process, if I want to study how the magnetization reverses in this, what happens is you reduce this magnetic field, you nucleate a vortex at one edge. That vortex propagates down to where in zero field it's here. As you continue to increase the field, it finally pops out the other side. There's an asymmetry in this, which I'm not going to, it's not important for this story, and I'm not going to go through it. But there's always an asymmetry in when the first vortex nucleates and what you got to do to get the last one out. So Pete was interested in this, and this was actually not his thesis project, but he wanted to do this on the side. And Pete worked 80 hours a week. So if he wanted to spend 20 hours a week doing something he thought was fun, who am I to say don't do it, right? So he did this on his own, which ultimately, after we started seeing things, became his thesis project. So he took these dots that were, this is 400 nanometers across, cut it out the middle and put it in a rectangle and made a stadium. Of course, you didn't do this, right? You made the stadium directly lithographically. You didn't take dots, cut them in half. Okay. But you can think of it as a dot as being cut in half and then sticking a rectangle in there. And it was easy to characterize it. Then you talk about the diameter of the dot and then the length of the rectangle that goes in the middle of it. So this is what we wanted to look at. Now, to give you an idea about these dots and why there was the interest in them at the beginning, if H is big applied field, I can make it saturate. In zero field, it looks like this. Now, it forms this because of that dipole-dipole interaction. That dipole-dipole interaction is long range. Remember I told you that on long length scales, because it falls off like 1 over r cubed, it can actually kick the exchange energy around a little bit, right? Because the exchange energy is a really short length scale. So it does this to minimize that dipole-dipole interaction energy on the surface of that dot. As I reach the center of that dot, now I'm looking at spins that are going this way, that way, that way, that way on an atomic scale, right? The exchange energy is on the order of 1,000 Kelvin. How big is that dipole-dipole interaction? Half a Kelvin? That's the wrong trade-off. And in fact, what happens in the very center of the dot, the exchange energy takes over and it pops the magnetization either out of the plane or into the plane. So you actually get right in the very center, you'll have a little pole that either sticks out or into the plane from that exchange energy. So it's a marvelous trade-off between these two, between the dipolar coupling and the exchange coupling. And it all comes about from those different length scales. So here, I want to reinforce this again. Blue is up, green is left, yellow is down, red is to the right? Just to learn that color scheme. Now, when we make small stadia, so this is one, this was like, so it's on this, it's like 300 nanometers. So the length of the rectangle in here is like 300 nanometers. And these are actual MFM images. So this is where we're running our finger over those stadia. And since you're only sensitive to magnetism, you don't know where these things are. So we put the dotted lines around here to show you where the particles are. And the only thing I want to show you from here is that this, looking at these images and trying to decide what it is, one thing, it tells you the importance of doing the simulations, because I'll show you in the next slide that the simulations actually predict what you see. And so we have a one-to-one correspondence there to actually know what we're looking at. But here what I want to show you is that just by the symmetry here, let's say the magnetization is going counterclockwise here. It's going counterclockwise here. In the very center, we have that magnetization that either points out of the plane or into the plane at that very center. And if you look, this color is light and that color is dark. Now in the MFM images, dark means, by convention, for VICO microscopes, dark means that it's attractive, where your finger is being pulled down. The light color means it's repulsive, means your finger is being pushed back. And if you look, that means here my finger is being pushed back, there my finger is being pulled in. That means we have opposite cores. So in one case, I have an outie, in the other case, I have an innie, in more childish language. So we can actually determine the sign of the cores in these vortices. If I look at the reversal for one of these small stadia, just like in the magnetic case, I will nucleate a vortex at one edge. So this is red now, so everybody's pointing to the right, and I want to get to this state where everybody points to the left. So I reduce the magnetic field, I nucleate a vortex, and it propagates across and pops out the other side. That's exactly the way you did it with the dots that I was showing you at the very beginning. No surprises here. The surprise is that, and I'll start you out in zero field, this is a small stadium. We go to a slightly bigger stadium. We only increase this by maybe 100, 200 nanometers. And this structure, these MFM images, look very different from these MFM images. And that's because these, which are simulated by this, come from this structure. I now have two vortices, one at each end, and an anti-vortex in the middle. Now remember, with my vortices, I have a core, because as the magnetization rotates around on ever smaller length scales, finally the exchange energy dominates, and so in the very middle I'll have a core that either pops out of the plane or into the plane. This anti-vortex that forms, if you notice here going around, these spins are all rotating as I go around, as I go to smaller and smaller length scales. I now get to a point where the exchange energy dominates for that, and I'll have a polarization in the middle here that also either sticks out of the plane or into the plane. In the case of the vortex, the chirality of the vortex, clockwise or counterclockwise, is completely independent of the vortex core. There's nothing that couples them, right? There's no surprise. And the same is true for the anti-vortex. This anti-vortex core can either point into the plane or out of the plane. And I can, by the way, I can also, just like I have two different looking vortices, you also have two different looking anti-vortices. I can flip all the spins in there and have something that looks a little bit different. But not much. That's sort of a swindle too, but that's okay. Here, yes? That's where we're headed. That's the meat of the problem. In this case, you mean, why do I have two vortices in this anti-vortex? Is that the question? Yep, we're coming to that. Actually, your question is not. It's not something I'm going to do. So, in this process here, let me go back. In this process here, where I nucleate a single vortex, I've reduced the field now, and what I end up having here is a bunch of spins that are still pointing against the direction of the magnetization, and so that's costing me energy. But this is going to be a lousy explanation. But I have to live with it because things are too confined. This will be maybe it's let me get to the end, and then we'll come back to your question, because I think whenever some of the stuff I get to at the very end might be an easier way to explain it. It's a good question though, because I can tell you other things we've tried to do that just doesn't work the same way. Okay, so here's the structure. If I have a small aspect ratio stadia, I nucleate this one vortex and it propagates across to reverse the magnetization. The surprise was, and this is when I got real excited about the problem, when I increased the length of that stadium just a little bit, so here I've gone from 300 to 500 nanometers, and this threshold, we tried to see how sharp this transition was, and it's not as sharp as I would have guessed. So there's probably all kinds of defects and other things that can play games with this. But you don't increase it much, and now it's saturated, so green means everything is pointing to the left. I'm dropping down. I've now nucleated a vortex, and it starts to propagate from one end to the other, just like over here. But before it even gets to the middle, all of a sudden, boom, I get this vortex-anti-vortex pair that's created out of space. So this is when I got excited about this, was because in many physical processes, right, the vacuum state is full of particle-antiparticle pairs, and for certain effects in atoms and things like that, you can actually probe the vacuum state, right? So I thought, we're doing this. This is we're looking at stop action field theory here, and it turns out that that's more of a stretch than I had hoped for. But just like in the physical processes you have like that, I nucleate this particle-antiparticle pair. The antiparticle annihilates with the original particle. The leftover particle finishes the process, the physical process that's going on. So it finishes the magnetization process. So this is the way, as you get the longer aspect ratio stadia, you always have this vortex-antivortex pair spontaneously created. The antivortex annihilates with the original vortex, and the leftover from the pair propagates across. You will also notice here I've drawn this so that this has a core polarization in one direction. The vortex anti-vortex pair I've drawn here have a core polarization in the opposite direction. In the simulations, this is what you always see. Experimentally, you always see this, but sometimes these two core polarizations match with that. And we can talk about that if anybody's interested, but it just comes from the fact that our magnetic field is not perfectly aligned with the plane of the samples. If we had exactly the right geometry, I'm convinced that it would always be like this, because we've actually intentionally done this to make sure that we can make it so that they always have the same sign. Now, this thing, I told y'all that this annihilates and this one goes on across. So now what annihilates here is a vortex anti-vortex pair that have opposite core polarizations, right? But I can stop my magnetic field at this process and remagnetize it, and now it's this vortex and anti-vortex which annihilate, and they have the same core. So I can actually annihilate these two or these two, just depending upon what I do with my magnetic field after I reach this point. Now, this is the distance from the end of a stadium, and this is the applied field. So somewhere over here where the sample is saturated, so it's in a single domain, and we've nucleated a vortex and it propagates. So it starts out at the end and it's coming in. And then somewhere at some field above zero, we get the nucleation of the anti-vortex and the vortex pairs. Then we continue magnetizing it, and in this continued process, so I'm keeping the field moving in the same direction, this anti-vortex and this vortex annihilate each other, and I complete the magnetization reversal with this other vortex. Okay. Now, there's some things in here that are filled triangles and others that are empty. These are not simulations, by the way. This is real data. It turns out that I can have my cores that annihilate, if it's the red and green ones, have the same core magnetization. That's when I reverse the field and go back from where I came. Or the opposite polarization. And if you look, the filled circles here are where they have the same core polarization, and they annihilate here at this field. The ones that have unlike cores go all the way up to here. So we're not talking about a small effect, right? This is not a 5% effect I'm looking for, a 3% effect. In this case, if they have opposite cores, the field required was 260 Oersted. If they have the same cores, it's 180 Oersted. The question is, why is the asymmetry? This is a hand-waving argument. If I imagine that I had the same core polarization, so now this is a vortex core pointing up, so my film plane is in this direction, okay? So the cores are perpendicular to the plane. This is up and this is up, and halfway between them, the magnetization lies in the plane. As I push those two together, the magnetization in the middle will lift up until finally they annihilate. If they have opposite polarizations, this is the one that requires bigger field, I'm now compressing a domain wall. I'm actually compressing this up to down, and as I get these two close to each other, that's costing me more and more and more exchange energy, and that's a big energy, and that pushes them apart. So this is a hand-waving argument. The trouble is, when we do the simulations, we can track the energies as they come down, and the blue is where they have the same core polarizations, and the red is where they have opposite. You don't see anything in the energies. You break this up and you look at the Dmag energy, you look at the exchange energy, you look at the Zeeman energy. You can't track anything. And this is the total energy that we're calculating here as a function of the vortex anti-vortex pair separation. So like cores and opposite cores, they follow the same number down. And this is the place where I was stuck because I didn't have any, to me, I had no smoking gun. I had no, other than a hand-waving argument, there was no real explanation for this. And this was when I was, a month or so ago, when I started working on the talk before coming down here, I had remembered somebody, it's a theorist at Johns Hopkins that I was talking to, and he said, oh, you know what, maybe it has to do with the Skyrmion number. What's this? I had no idea what this was. So, what can it be? Skyrmion physics. Right. If we're looking for buzzwords, there you go, huh? This has got to be PRL, right? That's with a name like Skyrmion. So this is from Chaoling Chen and a couple of co-workers' article in Physics Today back in 2007. This is what Wikipedia says it is. So normally I'm like my students. I look up Wikipedia. A skyrmion is a homotopically non-trivial classical solution of a nonlinear sigma model with a non-trivial target manifold topology, a particular case of a topological soliton. I got real bummed out when I read that. I thought, I've got no chance, right? I don't even have theorists at Minnesota, I think, that could handle this one. So, but in Chaoling, this did not come from Chaoling's article. So, but in Chaoling's article, what he does, he talks about, here's 3 vortices and here's an anti-vortex. Those are the ones that I drew for you earlier. P is the core polarization, and I can pick a core. I can say out of the board is 1, into the board is -1, right? Who cares? So this one, this core polarization is 1. This one, this core polarization is -1. This one, this core polarization is 1. This one, for the anti-vortex, this polarization is -1. N is my winding number, and my winding number doesn't depend upon the chirality of the vortex. So this is not like superconducting vortices. So here, this is going counterclockwise, this is going counterclockwise, this is going clockwise, and they all 3 have the same winding number, 1, 1, 1. The anti-vortex has a winding number of -1. This skyrmion number, Q, is the winding number times the chirality divided by 2. So in this case, this times this is 1, divided by 2 is a half. This times this is -1, divided by 2 is -1/2. This times this is 1, divided by 2 is a half. This times this is 1, divided by 2 is a half. Okay? So I have winding numbers, and I need to conserve winding numbers. So if I take, so there's a barrier against if you don't conserve your winding numbers. So in fact, here's my winding number is 1. My skyrmion number is a half. Here for this anti-vortex, the winding number is -1. The skyrmion number is a half because this core polarization is opposite. So -1 times -1 is 1 divided by 2, so it's a half. So annihilation does not conserve Q. Turns out that for topological defects, you have to conserve the winding number and the skyrmion number. Those are the 2 things that you have to worry about. So here, now I've got the same core polarizations. Here my winding number is 1. My skyrmion number is -1/2. Here my winding number is -1. My skyrmion number is +1/2 because now I've just, in this case, it's the same as that one was. So all I've done here is to flip that core, and I've gotten this to be -1/2, this is a half. Now, when these annihilate, it conserves both the winding number and the skyrmion number. So this should be a process that's physically allowed. So the other process, it's not allowed, and so you have to push on it, you have to violate what it's doing to be able to destroy it. So this is where I am now in my understanding of this problem, which is not completely done yet. But what it says in summarizing this, I can use geometry and applied fields to create and study model systems for magnetic reversal. So that was part of this, which is something that we do. What we found was that in the reversal process, past the critical aspect ratio, the vortex-anti-vortex pair creation and annihilation facilitates the reversal. Understanding the vortex-anti-vortex and nucleation annihilation is not as simple as we thought. Associated energies do not vary so much. Somewhere it's hidden in the dynamics, but maybe the skyrmion physics is the answer, right? That's where I'm headed now. This process in general, the Kosterlitz-Thouless transition that occurs, has to do with topological defects, right, that have winding numbers of plus and -1. So we see it, so we're actually looking at it in terms of this. Cross-tie walls in magnetic systems, a cross-tie wall is made up of nothing but vortex, anti-vortex pairs all strung together. This is for art. If you look in the textbooks, all the textbooks draw cross-tie walls with the core polarizations up, down, up, down, up, down as you go from vortex to anti-vortex. According to what we've seen in the way they spontaneously nucleate, a vortex-anti-vortex pair always had the same core polarizations. And so I would guess that, in fact, if you look at cross-tie walls carefully, you would find that they actually, if they oscillate at all, they come in pairs. And it turns out there's one textbook that, in fact, they do it the way I'm saying, where the vortex-anti-vortex pairs have parallel polarizations. And that's in Alex Huber's book, with Alex and Rudy Schaefer, that book. They actually do them in pairs. And it's too bad that Alex is dead, because I'd like to know what he was thinking about when he drew that. Sure. Correct. Correct. Right. So in some sense, you can go back to the hand-waving argument that I used for a long time with compressing a wall versus no wall. And the thing that's sort of weird about that is that I still have, what they say actually is that, it would be interesting to see, they say that whenever you take the ones that don't conserve skyrmion number, you get a burst of magnons out. But the ones that do conserve it, where the field is all perpendicular, nothing, magnons don't pop out. But I don't understand, I don't quite understand how that cannot also generate a burst of magnons. But that's the claim. The claim is that this comes out in a burst of magnons whenever these things annihilate. The other thing, of course, is the cuteness factor. This is where I have particle-antiparticle pairs. It's like what you have in vacuum state processes that occur. And it's also not unlike the Casimir effect. This comes back to your question now. So now we're looking at excitations in a system that depend upon the geometry. And the geometry dictates what's allowed and what's not allowed. So if I have a long enough stripe, I can imagine it to get rid of the we know this happens in soft materials. You'll have a cross tie wall that goes all the way down the length, right? And so what we see depends upon that geometry and sort of the length of the system and what's allowed and what's not allowed. So it's not the best answer in the world, but it's an answer. Okay, so I don't do this, so I'm sure that if you talk to somebody that really specialized in cross tie walls, for example, they could give you a more energetic answer than that. But the way I look at it is it's in terms of it's like the Casimir effect, where it's the geometry that determines what fluctuations are allowed and not allowed in this case. So with that, I thank you very much. Yes, sir. This I thought we could make systems where we could evolve to actually study cross tie walls being formed. Turns out the particles get big enough that you get all kinds of domains that form, and you don't get the nice vortex-anti-vortex pairs. So it wasn't as clean as I thought it would be. Oh, God, if I didn't make that clear, I apologize. So here's my particle. We apply magnetic field to saturate it in perpendicular to the long axis. Then we just reduce that magnetic field. And so as we reduce that magnetic field, we're reducing the Zeeman energy that's holding it in that direction. So you're now developing poles, and those poles nucleate this vortex then. Should have stopped me during the talk and asked. Yes? So we've done simulations. So this is another thing we've been doing, and I've sort of lost energy in some sense. But we do the simulations, and doing the simulations takes maybe, I don't know, hour or two of computer time. And then what we did, we decided the time steps were too big. So we started doing smaller time steps, which makes it take longer. So we started trying to pre-configure the spin nodes. We'd stop with the spins in a certain configuration, then do smaller time steps. Trouble is, every time we go to smaller and smaller time steps, between one time step, there's nothing there. The next time step, everything is there. It's really quite, we've never been able to make small enough time steps to be able to see it. But we haven't gone down to something ridiculous either, right? I finally got tired of it. It was clear to me at some point I wasn't going to understand the physics by doing it that way. So that was part of at least my rationale for losing interest in doing it. Yes?
So what is the application for this the ring wall move and
I'm a physicist. Actually, what people claim is that you can use the skyrmion number, for making memory systems. Who knows? You happy now? They do, look. No, the trouble is, this is curiosity-driven research. We were wondering what was going to happen, and there was no application at all in mind whenever we did it. So I tell people often that my research is worthless. Yes? For example, if there's no other questions, I've got questions. What's the separation between magnetic poles? 2 millimeters. How did you decide that? How can you see where it repels? Can you really see that? You got good eyes. See, for me, that was normally what will happen is that people will give me a number of like 3 or 4 millimeters, because you're sensitive to when the tip gets pulled down, right? But you know that means it's being pulled down by north poles, for example. There's no such thing as a monopole, so there's got to be south poles in there somewhere, and it's other stripes halfway between, right? So what's the magnetization pattern in the card? So if there's only field on one side, right? It's like horseshoes, right? So take horseshoes and you make a string of them, and now I've got a line of north poles, a line of south poles, and on the bottom I got nothing. Now, why is that so important when you make these cards? What if you had magnetization poles on both sides? Then it would stick on the refrigerator either way, and the company's logo would be stuck against the refrigerator. You got to think outside the box on this one. Huh? Yes. So now to let y'all see these things, actually, the other thing is a more technical reason is it minimizes the demag energy, so you can use cheaper magnetite. Get out your card. Now, I'm going to put this on there, and I want you to go, wow. No, shh, wait a minute. This is just a private conversation. Don't use, okay?
turn the mic back on.
Wow. Here. So take one of these. They're back to back, and they're expensive, sort of. So I'm about to show you, because now he's become a buddy of mine now. Yeah, it's something like that. It's like, I mean, you can see whatever it is, the distance between the dots. But it was clear your number was close enough that it wasn't. You weren't just looking at where it was being pulled down. So I know I'll probably run out of time. David's standing there. This guy, Joe Stupak, I used to buy sheets from him at Orsted Technologies, and then when I had this IEEE lectureship, it was clear I was going to go broke buying plastic buying viewing sheets from Joe. And so everybody get a green sheet? No? Yeah, you're sitting at the back of the class again. Oh, there we go. How many do you have? You didn't get one? You're sitting at the front. Students at the front always get them. Anyway, so I want to thank Joe for this, and he is an extremely interesting man. That's I'll save him for dinner. So.
He's actually my opponent in one of the lawsuits.
Really?
Magnetic therapy, where you put the magnet on your knee and it makes you feel better.
And Joe was on the wrong side of that? Oh, I'll have to ask Joe about that one. You can't disprove it.
Yeah, but you don't have to answer that question. You only have to know whether they violated the patent of the other company. Whether it works or not is completely irrelevant.
Oh, is that? Oh my gosh. Anyhow, so, okay, now I'm done. Everybody got them. Everybody got green sheets. Okay, yep.